This paper presents an advancement in sequence processing models through Kolmogorov-Arnold Networks. The authors introduce seqKAN, which aims to preserve the interpretability and controllability benefits of CANs while handling sequential data more effectively. Their architecture shows remarkable extrapolation abilities compared to traditional RNNs, LSTMs. CANs differ from traditional neural networks by using learnable functions instead of weighted connections. Each edge in a CAN transforms its input using a combination of learned splines and a SILU activation function. This approach results in fewer, more interpretable parameters compared to the highly distributed representation of MLPs. Figure 1 illustrates the basic structure of a CAN network. CANs transform inputs through unique functions for each connection. For example, input x1 passes through two different functions for the two output nodes. The value at each output node is simply the sum of these transformed inputs without additional weighting. seqKAN implements recurrency purely within the CAN framework. This approach preserves the interpretability advantages of CANs throughout the entire architecture. By avoiding the incorporation of traditional neural network components with fixed activation functions and trained weights, seqKAN ensures that learned patterns remain accessible and modifiable. Figure 2 reveals the recurrent structure of seqKAN. At each time step, the current input and previous hidden state are passed through the hidden state layer to compute the new hidden state. This state, along with the previous input, then passes through the output layer to generate predictions. This design explicitly maintains previous inputs rather than assuming the hidden state can capture all relevant information. The authors designed an evaluation task based on pendulum physics with a time-varying string length. This creates a non-stationary sequence where models must implicitly discover the hidden variable, string length, to make accurate predictions. Figure 3 provides an insight into what seqKAN actually learned. The connection strengths, indicated by shading, reveal which inputs most influence each output. For the energy change prediction, we see the model discovered the critical relationship between angular velocity and energy. The plot shows remarkable correlation between the expression learned by seqKAN and the expected physics model. This correlation extends into the extrapolation region, beyond time step 200, indicating seqKAN truly captured the principle rather than memorizing patterns. This explains its superior extrapolation performance. While other models struggled to generalize beyond their training data, particularly on the complex energy prediction task, seqKAN maintained high accuracy. This suggests it successfully identified the underlying patterns governing the system dynamics, including the hidden variable, string length. The comparative analysis also reveals interesting insights about network design choices. The paper demonstrates that seqKAN represents a significant advancement in sequence processing, combining the interpretability benefits of CANs with performance that exceeds traditional approaches. The authors highlight both the strengths and limitations of their approach, particularly noting the challenges of representing multiplicative relationships in an additive network. Their future work directions address these limitations while building on seqKAN's core strengths.